just recalling some of the notation we're going to need for today, and a couple of the facts that we're going to use. So P of D plus a couple of, trying to clear up a couple of confusions of the recitations report. This can be thought of two ways. It's a formal polynomial in D in the letter D. It just has the shape of a polynomial, D squared plus AD plus B. A and B are constant coefficients. But it's also, at the same time, if you think what it does, it's a linear operator on functions. It's a linear operator on functions like y of t. You think of it both ways. Formal polynomial because we want to do things like factoring it, substituting 2 for d and things like that. Those are things you do with polynomials. You do them algebraically. You can take the formal derivative of a polynomial because it's just sums of powers. On the other hand, as a linear operator, it does something to functions. It differentiates them, multiplies them by constants, and something like that. So it, so to speak, has a dual aspect this way, and that's one of the things we're exploiting when we use operator methods to solve differential equations. Now, let me remind you of the key thing we were interested in, f of t, not any old function. We'll get to that next time, but f of t exponentials. So it should be an exponential or something like an exponential or pretty close to it. For example, something with sine t and cosine t, or e to the, that can be thought of as part of the real or imaginary part of a complex exponential. And maybe by the end of today, we'll have generalized that even a little bit more. But basically, I'm interested in exponentials. Let's make it alpha complex. That will at least take care of the cases e to the ax times cosine bx sine tx, which are the main cases. Those are the main cases. Then, remember the little table we made? I simply gave you the formula for the particular solution. So we want, what we're looking for is, we already know how to solve the homogeneous equation. What we want is that particular solution. And then the recipe for it I gave you. These things were proved by the substitution rules and exponential shift rules. The recipe was that if f of t was, well, let's make a little table. F of t is, well, it's always e to the at. So let's not. So in other words, it's e to the at. The cases are, so yp, what is the yp? Well, it is, the normal case is yp equals e to that alpha t divided by the polynomial where you substitute, you take that polynomial, and wherever you see a d, you substitute the complex number alpha. There I'm thinking of it as a formal polynomial. I'm not thinking of it as an operator. Now, this breaks down, so that's the formula for the particular solution. The only trouble is it breaks down if p of alpha is 0, so we have to assume that it's not. Now, if p of alpha is 0, that means alpha is a root of the polynomial. A 0 of the polynomial is a better word. So, in that case, it will be e to the alpha t divided by p prime of alpha. Differentiate formally the polynomial, so you'll get 2d plus a, and now substitute in the alpha. And this will be okay, provided that p prime of alpha is not 0. That means that alpha is a simple root, simple 0 of p. And then there's one more case, which since I won't need today, I won't write on the board, but you'll need it for homework, so make sure you know it. In other words, if this is 0, then you got a double root, and there's still a different formula. And this is wrong because I forgot the t. Yes. I could tell in your faces. Okay. And now we get to, that was before, and now we're up to today. What we're interested in talking about today is what this has to do with the phenomenon of resonance. Everybody knows at least one case of resonance, I hope. You know, a little kid is on a swing, right? Bing, back and forth, and they're very, very little, so they want to push. Okay. Well, everybody knows that to make the swing go, a swing has a certain natural frequency. It swings back and forth like that. It's a simple pendulum. It's actually damped, but let's pretend that it isn't. Everybody knows you want to push a little kid on a swing so that, you know, they go high. You have to push with essentially the same frequency that the natural frequency of the spring, of the swing is. In other words, now it's automatic because when you come back here, it gets to there, and that's when you push. So automatically you time your pushes. But if you want the kid to stop, you just do the opposite. You know, you push at the wrong time, and anyway. Okay, so that's resonance. Of course, there are more serious applications of it. It's what made the Tacoma Bridge fall down, and I think movies of that are now being shown, not merely on television, but in elementary school. Resonance is what made, okay, more resonance stories later. So my aim is, what is this physical phenomenon that to get a big amplitude, you should have to match the frequency? What has that to do with the differential equations? Well, the differential equation for that simple pendulum, let's assume it's undamped, will be of the type y double prime plus, I'm using t now since t is time, that will be our new independent variable, plus omega naught squared is the natural frequency of the pendulum or of the spring or whatever it is that's doing the vibrating. And now, what would, yeah, question? Any questions? What we're doing is driving that with the cosine with something of a different frequency. So this is the input, or the driving term as it's often called, or sometimes called the forcing term. And the point is, I'm going to assume that the frequency is different. The driving frequency is different from the natural frequency. So this is the input frequency. Okay, and now let's simply solve the equation and see what we get. So it's, if I write it using the operator, it's d squared plus omega naught squared applied to y is equal to cosine. It's a good idea to do this because the formulas are going to ask you to substitute into a polynomial. So it's good to have the polynomial right in front of you to avoid the possibility of error. Well, really what I want is the particular solution. It's the particular solution that's going to give me a pure oscillation. And the thing to do is, of course, since this is cosine, you want to make it complex. So we're going to complexify the equation in order to be able to solve it more easily and in order to be able to use those formulas. So the complex equation is going to be d squared plus omega naught squared times, well, it's going to be a complex particular solution, so I'll call it y tilde. And on the right-hand side, that's going to be e to the I omega 1t. Cosine is the real part of this, so when we get our answer, we want to be sure to take the real part of the answer. I don't want the complex answer. I want the real, its real part. I want the real answer, in other words. The really real answer. The real answer. Okay. So now, without further ado, because of those beautiful, the problem has been solved once and for all by using the substitution rule. I did that for you on Monday. The answer is simply e to the I omega 1t divided by what? This polynomial with omega 1 substituted in for d. So it's, sorry, I omega 1, the coefficient, complex coefficient of t. So it is substitute I omega for d, I omega 1 for d, and you get I omega 1 squared plus omega naught squared. Well, let's make that look a little bit better. This should be e to the I omega 1t divided by, now what's this? This is simply omega naught squared minus omega 1 squared. But I want the real part of it, so let's, as one final last step, the real part of that is what we call just the real particular solution. So yp without the tilde anymore. And the real part of this, well, this is cosine plus I sine, and the denominator luckily turns out to be real. So it's simply going to be cosine omega 1t, that's the top, divided by this thing, omega naught squared minus omega 1 squared. In other words, that's the response. This is the input, and that's what came out. Well, in other words, what one sees is that regardless of what natural frequency the system wanted to use for itself, at least for this solution, what it responds to is the driving frequency, the input frequency. The only thing is that the amplitude is changed, and in a rather dramatic way, if omega 1, depending on the relative sizes of omega 1 and omega 2. Now, the interesting case is when omega 1 is very close to omega, the natural frequency. When you push it with approximately its natural frequency, then the solution is big amplitude. The amplitude is large. So the solution looks like the frequency, the input might have looked like this. Well, it's cosine, so it's sort of start up here. The input might have looked like this, but the response will be a curve with the same frequency and still a pure oscillation, but it will have much, much bigger amplitude. And it's because the denominator, omega naught squared minus omega 1 squared, is always 0. So the response will instead look like this. Now, to all intents and purposes, that's resonance. You're pushing something with approximately the same frequency, something that wants to oscillate, and you're pushing it with the same frequency, approximately the same frequency that it would like to oscillate by itself. And what that does is it builds up the amplitude enormously. Well, what happens if omega 1 is actually equal to omega 0? So that's the case I'd like to analyze for you now. Suppose the two are equal, in other words. Well, the problem is, of course, I can't use that same solution. It isn't applicable, but that's why I gave you, derived for you using the exponential shift law last time, the second version, when it is a root. So, if omega 1 equals omega naught, so now our equation looks like d squared plus omega naught squared, the natural frequency, y. But this time, the driving frequency, the input frequency, is omega naught itself. Then, the same analysis, you know, a lot of it is no, I better be careful. Better be careful. Let's go through the analysis again very rapidly. What we want to do is first complexify it and then solve. So the complex equation will be d squared plus omega naught squared times y tilde equals e to the I omega naught t this time. But now I omega is a 0 of this polynomial. That's why I picked it, right? If I plug in I omega 0, I get I omega 0 quantity squared plus omega naught squared. That's 0. So I'm in the second case because, so I omega naught is a simple root, simple 0 of d squared plus omega naught, that polynomial squared. Therefore, the complex particular solution is now T e to the I omega naught t divided by, well, divided by P prime where you plug in that root, the I omega naught. Now what's P prime? P prime is 2D, right? If I differentiate this formally, as if D were a variable, the way you differentiate polynomials, the derivative, this is a constant, and the derivative is 2D. So the denominator should have 2 times, for D, you're going to plug in I omega 0. So it's 2I omega 0. And now I want the real part of that, which is what? Well, think about it. The top is cosine plus I sine. The real part is now going to come from the sine, right? Because it's cosine plus I sine. But this I is going to divide out the I that goes with the sine. And therefore, the real part is going to be T times the sine this time of omega t, naught t. And that's going to be divided by, well, the I canceled out the I that was in front of sine, the sine function. And therefore, what's left is 2 omega naught down below. So that's our particular solution now. Well, it looks different from that guy. It doesn't look like that anymore. What does it look like? Well, it shows the way to plot such things is basically it's an oscillation of frequency omega naught, but its amplitude is changing. So the way to do it is, as always, if you have a basic oscillation which is neither too fast nor too slow, think of that as the thing, and the other stuff multiplying it, think of as changing the amplitude of that oscillation with time. So the amplitude is that function t divided by 2 omega 0. So just as we did when we talked about damping, you plot that and it's negative on the picture. So this is the curve, the function whose graph is t divided by 2 omega naught. That's the changing amplitude, as it were. And then the function itself does what oscillation it can, but it has to stay within those lines. So the thing that's oscillating is sine omega naught t, which would like to be a pure oscillation, but can't because its amplitude is being changed by that thing. So it's doing this. And now the rest I have to leave to your imagination. In other words, what happens when omega naught is equal, when the driving frequency is actually equal to omega naught, mathematically, this turns into a different looking solution, one with steadily increasing amplitude. The amplitude increases linearly, like the function t divided by 2 omega naught. Well, many people are upset by this slightly in the sense that there is a funny feeling. How is it that that solution can turn into this one? If I simply let omega 1 go to omega 0, what happens? Well, the pink curve just gets taller and taller, and after a while, all that you see of it, is just a bunch of vertical lines which seem to be spaced at whatever the right period is for that function. Sort of like being in a first-story window and watching a giraffe go by. All you see is that. Okay. So my concern is, how does that function turn into this one? Now I have something in mind to remind you of, and that's why we'll go through it's a simple exercise, but the function of it is, of course, that as omega 1 goes to omega 0 cannot possibly turn into this. It's doing the wrong thing near 0. It's already zooming up. But the point is, this is not the only particular solution on the block. Any solution whatsoever of the differential equation, the inhomogeneous equation, is a particular solution. It's like Fred Rogers, everybody's special. Okay, So all solutions are special. We don't have to use that one. So I'll use, where are all the other solutions? So I'm going back to the equation d squared plus omega 0 squared applied to y is equal to cosine omega 1t. Now, the particular solution we found was that one, cosine omega 1t divided by that omega naught squared minus omega 1 squared. But what do the other particular solutions look like? Well, in general, any particular solution will look like that one we've found. What is it? Omega naught squared minus omega 1 squared. Plus, I'm allowed to add to it any piece of the complementary solution. In other words, equally particular and equally good as a particular solution is this, plus anything which solves the homogeneous equation. Now, all I'm going to do is pick out one good function which solves the homogeneous equation, and here it is, minus. It's the function minus cosine. In fact, what does solve the homogeneous equation? Well, it's solved by sine omega naught t, cosine omega naught t, and any linear combination of those. So out of all those functions, the one I'm going to pick is cosine omega naught t, and I'm going to divide it by this same guy. So this is part of the complementary solution. That's what we call the complementary solution, the solution to the associated homogeneous equation, to the reduced equation. Call it what you like. So this is one of the guys in there, and I'm allowed to, it's still a particular solution, to take the one I first found and add to it anything which solves the homogeneous equation. I showed you that when we first set out to solve the inhomogeneous equation in general. Now, why do I pick that? Well, I'm going to now calculate what's the limit. So these guys are also good solutions to that. This is a good solution to that equation, this equation. All I'm going to do now is calculate the limit as omega 1 approaches omega 0 of this function. Well, what is it? It's cosine omega 1t minus cosine omega 0t divided by omega naught squared minus omega 1 squared. Now, you see why I did that. If I let just this guy, omega 1 approaches omega 0, I get infinity. I don't get anything. But this is different here because I've fixed it up now. The denominator becomes 0, but so does the numerator. In other words, I put myself into position to use L'Hopital's rule. So let's L'Hopital it. It's the limit of omega, as omega 1 approaches omega 0. And what do? You differentiate the top and the bottom with respect to what? Right, with respect to omega 1. It's the omega 1 is the variable. That's what's changing. The t I'm thinking of is for the temporarily fixed, a fixed value. This has a fixed value. Omega naught is fixed. All that's changing in this limit operation is omega 1. And therefore, it's with respect to omega 1 that I differentiate it. You got that? Well, you're in no position to say yes or no, so I shouldn't even ask the question. But okay, rhetorical question. All right. Let's differentiate this expression, the top and bottom with respect to omega 1. So the derivative of the top with respect to omega 1 is negative sine omega 1t, but I have to use the chain rule. That's differentiating with respect to this argument, this variable. But now I must take times the derivative of this thing with respect to omega 1, and that is t is the constant, so times t. And how about the bottom? The derivative of the bottom with respect to omega 1 is, well, that's a constant, so it becomes 0, and this becomes negative 2 omega 1. So it's the limit of this expression as omega 1 approaches omega 0, and now it's not indeterminate anymore. The answer is the negative signs cancel. It's simply t sine omega naught t divided by 2 omega naught. So that's how we get that solution. It is a limit as omega 1 approaches it, but not of the particular solution we found first, but of this other one. Now, it's still too much algebra. I mean, what's going on here? Well, that's something else that you should know. Okay, so my question is, therefore, what does this mean? What's the geometric meaning of all this? In other words, what does that function look like? Well, that's another trigonometric identity, which is, in your book, it's just buried as half of one line, you know, sort of casual, as if everybody knows it. And I know that virtually no one knows it. But here's your chance. So the cosine of B minus the cosine of A can be expressed as a product of sines. It's the sine of A minus B over 2 times the sine of A plus B over 2, I believe. My only uncertainty is there a 2 in front of that. I think there is. I think there has to be. Let me check. Sorry. Is there a 2? You know, I wouldn't trust my memory anyway. I'd look it up. I did look it up. 2, yes. If you had to prove that, you could use the sine formula to expand this out. That would be a good bad way to do it. Best way is to use complex numbers. Ta-da. Express the sine in terms of exponentials. You know, the backwards Euler formula. Then do it here, and then just multiply those two expressions involving exponentials together, and cancel, 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 and this is what you'll end up with. You see why I did this? It's because this has that form. So let's apply that formula to it. So what's the left-hand side? So B is omega 1t, and A is omega naught t. So this is omega 1t, and this is omega naught t. All right. So what we get is that the cosine of omega 1t minus the cosine of omega naught t, which is exactly the numerator of this function that I'm trying to get a handle on, then we'll divide it by its amplitude, so that's this constant factor. That's real. It's a small number because I'm thinking of omega 1 as being rather close to omega 0 and getting closer and closer. But what does this tell us about the right-hand side? Well, the right-hand side is twice the sine of A minus B. Now that's good because these guys sort of resemble each other. So that's omega naught minus omega 1 times t. That's A minus B, and I'm supposed to divide that by 2. And then the other one will be the same thing with plus. Sine omega naught plus omega 1 over 2 times t. Now, how big is this approximately? Omega, remember, think of omega 1 as close to omega 0. Then this is approximately omega 0. So this part is approximately the sine of omega 0 t. This part, on the other hand, that's a very small thing. Okay, now, what I want to know is, what does this function look like? The interest in knowing what that function looks like is because we want to be able to see that its limit is that thing. You can't tell what its limit is geometrically unless you know what it looks like. So what does it look like? Well, again, the way to analyze it is this thing, that thing. What you think of is yeah, of course, you cannot divide one side of an inequality of equality without dividing the equation by the other side. So that's got to be there too. Now, what does that look like? Well, the way to think of it is, here is something with a normal sort of frequency, omega naught. You know, it's doing its thing. It's the sine curve. It's doing that. What's this? Think of all this part as varying amplitude. It's just another example of what I gave you before. Here is a basic pure oscillation, and now think of everything else that's multiplying it as varying its amplitude. All right, so what does that thing look like? Well, first what we want to do is plot the amplitude lines. Now, what will they be? This is sine of an extremely small number times t. The frequency is small. How does a sine curve look if its frequency is very low, very close to 0? Well, that must mean its period is very large. Here's something with a big frequency. Here's something with a very, very low frequency. Now, with a low frequency, it would hardly get off the ground and get up to 1 here, and it would do that, but it's made to look a little more presentable because of this coefficient in front, which is rather large. And so what this thing looks like, I won't pause to analyze it more exactly. It's something which goes up at a reasonable rate for quite a while, and let's say up, that's quite a while, and then it comes down, and then it goes, you know, and so on. Of course, in figuring out its amplitude, we have to be willing to draw its negative too, and since I didn't figure things out right, I can at least make it cross right. Okay. So this is a picture of this slowly varying, of this varying amplitude. And in between, this is the function which is doing the oscillation as well as it can, but it has to stay within that amplitude. So it's doing this. Now what happens? As omega 1 approaches omega 0, this frequency gets closer and closer to 0, which means the period of that dotted line gets further and further out, goes to infinity, and you never do ultimately get a chance to come down again. All you can see is the initial part where it's rising and rising. And that's how this curve turns into that one. Now, of course, this curve is enormously interesting. You must have had this somewhere. That's the phenomenon of what are called beats. Two frequencies, which your book has a half a page explaining this. That's the half a page where he gives you this identity. Except it gives it in a wrong form so that it's hard to figure out. But anyway, the beats are two frequencies. When you combine them, the two frequencies being combine two pure oscillations where the frequencies are very close to each other, what you get is a curve which looks like that. And of course, what you hear is the envelope of the curve. You hear the dotted lines. You don't hear, well, you hear this, you hear that too, but what you hear is, that's how good violinists and cellists and so on tune their instruments. You know, they get one string right, and then the other strings are tuned by listening. They don't actually listen for the sound of the note. They listen just for the beats. Wah, 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 and they turn the peg, and that goes wah, 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 wah. And finally, until the wahs, as soon as the wahs disappear, they know that the two strings are in tune. A piano tuner does the same thing. Of course, I, being a very bad cellist, use a tuner. That's another solution, very modern, a more modern solution. Okay. Oh, well, let's give it a try. The bad news is that on problem 6 in your problem set, I didn't ask you about the undamped case. I thought since you are mature citizens, you could be asked about the damped case. I warn you, first of all, you have to get the notation. This is probably the most important thing I'll do with this. Your book uses this. Resonance. I'm optimistic. Let's say 0 or f of t. It doesn't matter. Some functions. In other words, the constant, the book uses two sets of constants to describe these equations. If it's spring, I'm not even talking about RLC circuits. For the spring, mass, damping, K, spring constant. Then you divide out by m and you get this. You familiar with that? And it's only after you've divided out by the k, by the m, that you're allowed to call this the square of the natural frequency. So omega naught is the natural frequency, the natural undamped frequency. If this term were not there, that omega naught would give the frequency with which the system would like to, the little spring would like to vibrate by itself. Now, further complication is that the visual uses neither of these. The visual uses x double dot plus b times x prime. I think we'll have to fix this in the future, but for now, just live with it, plus kx, and that's some function, again, a function. So in other words, the problem is that B is okay, can't be confused with C. On the other hand, this is not the same K as that. Because this K, to be converted in the, either you have to assume the mass is 1, or you have to divide through by it, in which case. So what I'm trying to say is don't automatically go to a formula one place and make it, assume it's the same formula in another place. You have to use these equivalences. You have to look and see how the basic equation was written, and then figure out what the constant should be. Now, there was something called, when we analyzed this before, and if this has happened in recitation, there was the damped frequency. I'll call it the natural damped frequency. The book calls it the pseudo frequency. It's called pseudo frequency because the function, if you have 0 on the right-hand side but have damping, the function isn't periodic. It decays. It does this. Nonetheless, it still crosses the x-axis at regular intervals. Crosses the t-axis at regular intervals, and therefore almost everybody just casually refers to it as the frequency and understands it's the natural damped frequency. Now, the relation between them is given by the little picture I drew you once, but I didn't emphasize it enough. Here is omega naught. Here is a right angle. This side is omega 1, and this side is the damping. So in other words, this is fixed because it's fixed by the spring. That's the natural frequency of the spring by itself. If you have damping, if you're damping the motion, then the more you damp it, the bigger this side gets, and therefore the smaller omega 1 is. The bigger the damping, then the smaller the frequency with which the damped thing vibrates. That's sort of intuitive. And vice versa. If you decrease the damping to almost 0, well, then you'll make omega 1 almost the same size as omega 0. This must be a right angle. And therefore, if there's very little damping, this natural damped frequency will be almost the same as the original frequency, the natural frequency. So the relation between them is that omega 1 squared is equal to omega naught squared minus p squared, and this comes from the characteristic roots, of the damped equation. So we did that before. I'm just reminding you of it. Now, the third frequency which now enters and that I'm asking you about on the problem set is, if you've got a damped spring, okay, what happens when you impose a motion on it with yet a third frequency? So in other words, drive the damped spring. Let's X, I don't care. I switch to Y since I'm in a Y mode. So our equation looks like this, just as it did before, except now I'm going to drive that with an undetermined frequency, cosine omega t. And my question now is, see, it's not going to be able to resonate in the correct, you really only get true resonance when you don't have damping. That's the only time when the amplitude can build up indefinitely. But nonetheless, for all practice, and you never have, there's always some damping unless you're a perfect vacuum or something. There's always some damping, so P isn't 0, can't be exactly 0. So the problem is, which omega gives which frequency in the input, which input frequency gives the maximal amplitude for the response? We solved that problem when it was undamped, and the answer was easy. Omega should equal omega 0. But when it's damped, the answer is different. And I'm not asking you to do it in general. I'm giving you some numbers. But nonetheless, it still must be the case. So I give you a specific values of P and omega 0. That's on the problem set. Of course, one of them is tied to your tied to your recitation. But the answer is, I'm going to give you the answer, the general formula for the answer, because to make sure that you don't get wildly astray. Let's call that omega R, the resonant omega. This isn't true resonance. Your book calls it practical resonance. Again, most people just call it resonance and sort of, you know what I mean, Al, type of thing. It is omega R is very much like that. Maybe I should have written this one down in the same form. Omega 1 is the square root of omega naught squared minus p squared. What would you expect? Well, what I would expect is that omega R should be omega 1. The damped system has a natural frequency. Omega 1, the resonant frequency, should be the same as that natural frequency with which the damped system wants to do its thing. And the answer is that's not right. It is the square root. It's a little lower. It's a little lower. It is omega naught squared minus 2p squared. Okay, I think we better get out before, while we still can. At least this lecture will be safe.